Hi everyone, welcome to another episode of Scientific Modeling with Blase. In this video, I hope to introduce logic gates and multi-input activation repression models when it comes to gene expression. So in the last video, I talked about the Hill function and how it's a continuous model. Usually it's not a very steep step function. This is the repressor. We have the Y promoter activity and the activator X. It's actually a repressor X. This is what that should be. And so that the Y promoter, the target of the X, is only active at low concentrations of X. And so what if we have more than one activator or if we have different kind of gates associated with our output promoter? So logic gates are often used in computer science in terms of the zeros and ones, and so we can kind of model that in Python using that technique. Here's 5 of the basic ones. They left off the very first logic gate in this figure, which is just the yes gate, and that's just when there is a presence, then X is expressed. But in the not gate, it's the opposite. So A is not there implies that X is expressed, and if A is there, X is not, and so A would be acting as some sort of repressor. An AND gate would be X output is only happening under the presence of both A and B, and so A and B are working together in this instance to activate the X promoter. NAND gate would be everything except the AND output, and so it's active at all things except this. And then the OR gate, active whenever there is an A or B, so both A and B may be activators in this example. And then the NOR gate, where where A and B are both repressors, and thus X is only active when there is not any of them. We can do a good job visualizing this in Python. I'll show you how. What we use is mpl_toolkits, and from there we will import mplot3D. So in this, when we plot in 3D, I'll have an axis for the A concentration, axis for the B concentration, then the Z axis will represent our promoter activity of the target gene. I'm gonna deal with n equals 2, kn equals 1, beta equals 1, and really go off the fundamentals what we did here. I am making n louder. I am making the step function steeper, and so at n equals 2, we're just a little steep. We're not overly steep, but that's about where we'll be. Instead of 1, it's a lot more visually stimulating. Anyway, nothing new here, and if we just graph it, this all runs, and this is actually going to be an OR gate. And so the only time where there is no expression when there's right, so the Z-axis is going to be our target gene promoter's activity. And so the only time that it's not very active is when we're at 0, 0, the origin over here, because this is 0 and that's 0. So that's an AND gate, or sorry, this is an OR gate. An AND gate would look somewhat similar, except for it needs the concentration of both. And so you can kind of control the parameters of where the steepness is. But the idea being where it's only active when both A and B inducers are present. You can make this, of course, stronger, where it's like only under certain concentrations. And right, since we're modeling, we're just trying to represent in some sort of Python graph what a certain gene is going through or under certain circumstances. And so basically the gene, the difference between this and this is I'm just raising it to some power. Now let's talk really quickly about what I'm actually plugging in. And so I redefine my F vector that we will be graphing as Z to be the addition of two Hill functions, or it's really just the adding of two Hill function outputs. And then I divide by 2 so that our x value doesn't exceed 1. And so this is an activator, the Hill equation the activator Hill equation. This is similar, just this is for the concentration of x and this is the concentration of y. And so when we add them, we get an OR gate. And then if we multiply them, we get an AND gate, right? Because if one of them's 0, we're going to be along this 0 z value. And then, of course, if I want to make that stronger and I raise that whole thing to a power, we are going to get some sort of stronger representation of it. Again, I could just make this, I could tinker with this exponent value so that this could equal 1 on our x value or on our z value. It would just take a little bit more time than I'm willing to give to it. Now, so we just dealt with the activator Hill function. If we plug in the repressor Hill function, we'll get almost the reverse. So if I add the Hill function outputs, so this is now the Hill function output, right? And so we're going to get a variable like this, or some sort of three-dimensional depiction like this, where we're only active when there's 0 A or B influencers. And so that's right. If I look back at the code, I'm adding the Hill function output of 2 repressors. This is the repressor of x. This is the repressor of y. I divide it by 2 so that we don't exceed 1. Now, of course, I can make this stronger, but it turns out if I just multiply it, it makes it stronger. And so really it's only active if we have 0 of either in this case. And so this is just a NOR gate as well. It's just a little bit stronger when you multiply it. And so once you combine an activator with the, oh, I'm sorry, this is the repressor function, and this is the activator. It wouldn't matter if you swapped them or multiplied them. You get kind of a more funky distribution. And so it's kind of tough to model if you have using this three-dimensional method when it comes to actually just viewing this on three-dimensional depictions. Now, just to show you, I'll change this to a multiplication, and you'll see it's still, okay, very dependent on 1. However, right, like that's not, I don't think that's going to be a very accurate model for anything. This is probably more accurate, where if I have high concentrations for both, we'll have some sort of, I should divide it by 2 to normalize it to what we've been dealing with. But the idea being, where in this green area, there's an equally likelihood of it being active or repressed. But this doesn't model it that well. And so this leads us into actually introducing models that will actually be able to help us understand what's happening a little bit better when you have both an activator and a repressor in a system. You don't have to wait for my next video to view that, however. Anyway, I hope this helps you with three-dimensional plotting when it comes to having 2 or more influencers of a gene, as well as the understanding of logic gates. Thanks.